About kernel mode. It's going to be heavily technical, so please stop me if you don't understand anything. I don't want anyone to be lost, so I'm a friendly person. Just stop me. First of all, I would love to gather some data from the audience. How many of you guys are developers? 1, 2, 3, 4, 5. Testers? Okay, 1. Kernel mode, user mode, kind of. What kind of tests do you do for your applications, for your interfaces that you suppose? Do you fast? Do you do static analysis? Do you do something at all? Probably yes. Let's go to the bad guys. How many of you guys have ever developed an exploit? 1, 2, 3. Kernel one? Successful one? Kind of. Okay, thank you. So this is going to be fun then. How many of you have ever seen Windows source code? None? One? Do you guys really want to? No? Windows kernel source code. So I need some interaction then. I will explain later, but I need your help for the next slides. So this is going to be the agenda. There's going to be an introduction on kernel mode. Since I don't know the level, the knowledge level of you guys about kernel mode, I will start with the basics. We'll start talking about kernel mode versus user mode execution, kernel space versus user space, etc. And we'll start growing from them. I will show some common mistakes with fake source code. I will try to be detailed, and I will go through the source code, telling you where the vulnerabilities are. Later on, I will apply those mistakes to real MSRC cases. That's going to be the stage where we will see Windows source code. And at that point, I need your help because you are going to be the ones that will spot the bug. Okay? Then 1, 2, 3, 4, 5 people. I'm going to go for you. The latest stage is going to be detect, protect. What do I mean with this? Basically, I'm going to show several tools, several free tools that Microsoft provides that you can include in your development lifecycle to make your life easier and to detect these vulnerabilities early in the process, before you ship your product and before external people find those. And at the end of the time, if we have time, QA, okay? Any questions so far? Hopefully not. So who I am, I work for Microsoft, I work for MSRC. Anybody knows what MSRC is? Hopefully someone. 1, 2, 3, 4, okay. So MSRC basically is the security group of Microsoft. Whenever you guys report or find a vulnerability in any of our products, and hopefully you're going to report friendly to us, in a friendly manner to us, it will come to at least one engineer in my team. My team is the one that is responsible for verifying if it's a security vulnerability, verifying, triaging it, testing it, setting the exploitability, and if it meets the MSRC bug bar, it will get a bulletin for it. So I'm a security engineer in the MSRC Engineering React team, formerly known as SWI, Secure Windows Initiative. We're a technical background of MSRC operations teams. I've been dealing 3 years with a lot of cases, and for example, I was the one in charge of MS0867. Anyone familiar with this case? Configure, Net API. So I was the one that was handling this case on the React side. My role basically is to, as I already told, to triage, to set exploitability, to see if it's a valid issue, and to clean the area. Basically, we do a lot of fast testing, source code analysis, static analysis, looking for similar issues in order to clean the area. So I was in charge of this case, and in question of 2 weeks, I had to clean that area. Also, I love exploitation. I love exploitation on weird architectures, HPX, PARVISC. I've been doing this for 10+ years. If anyone has similar interest, drop me an email, come to me. I would love to have a beer with you. Well, this is me. I don't want to spend much time here. You can read it, okay? So, purpose of the talk, first of all, kernel mode. Whenever I talk to someone about kernel mode, they start saying, "Oh, kernel mode, man, you're crazy." It's not that obscure. It's similar to user mode. I mean, it's difficult, but it's not hell, right? So we have the similar problems in user mode. We have buffer overflows, integer overflows, small allocations, and later big copies, etc. And I don't want to talk about things that I cannot prove. So later on this presentation, I will prove them on real MSRC cases. And another thing that I want you to get from this talk is if you are a kernel developer, take security into consideration. At Microsoft, we are trying to. We are raising the bar, but we have a lot of third-party components that I would love to help you guys to increase the bar on those third-party components and provide tools, as I already told you. So we're going to start with the kernel basics. Who is familiar with kernel mode, user mode? Hopefully a lot, right? Yeah, 10? OK, that's good. So basically, there are two execution modes. Well, speaking correctly, there are not two, but well, let's say that there are two, user mode and kernel mode. And the 4 gigabytes virtual space is divided in two. I'm not going to talk about the 3 GB switch when initially when the boot options on Windows. I'm going to stick to this just for it's going to be simpler. So user mode has 2 gigabytes. Kernel mode has 2 gigabytes. There are two execution modes: kernel mode, user mode. How kernel mode can access its kernel mode space and the user mode space. User mode processes, when you're executing code in user mode, you can only access your user's mode virtual space. You cannot access kernel mode space, and you cannot access any other user mode, any other user processes virtual space. This is done by paging. Basically, the PD, PT tables in kernel mode, setting admin bits, you cannot access the kernel pages from when you're executing in user mode, and segmentation. And kernel mode and user mode, basically user mode communicates to kernel mode between through interfaces. Whenever, for example, let's say that a user application needs to get the color at I don't know XY position. The XY position gives me the color. The user process has not the ability, has not the access to go to the video mode to grab that color. So it has to go to kernel mode. Basically, user mode says, OK, kernel, give me this color, and kernel will return. So kernel needs to validate all the data, all the requests from user mode. We should treat all the user mode requests as untrusted. So we need to validate, we need to do all these checks that, for example, a user mode program will do for all the data that comes from a network. So similar to thing. Kernel mode should do all these checks for the data and requests that come from user mode. As I already told you, kernel space can only be accessed if you are executing in kernel in ring 0, and user space can be accessed in both. I already talked about the interfaces where user mode can make requests and communicate to kernel mode. These are a couple of them: software interrupts, shift center, the new mechanism, all interrupt into E stuff. Device I/O, basically to communicate to drivers through IOCTLs. User mode callbacks. This is being used by Win32k. It's a kind of different mechanism other than the software interrupts and device I/O. And of course, networking. There was another talk about USB, how external devices can communicate to the kernel. My talk is going to basically cover the three first. I'm not going to cover any others. Basically, I'm going to cover any user mode app trying to communicate to kernel mode. I'm not going to cover kernel mode trying to process a GMP packet or something like that. Well, probably yes. But I'm going to cover user mode to kernel mode. Any questions so far? I don't want anyone to be lost. We're going from the basics. No? OK? Yes? No? Let's go. So an entry point example. Let's say set w fake get me color at pixel has 3 arguments, ulong x, ulong y, and a pointer to a buffer to get the color, right? This is going to be executed in kernel mode, but the parameters are supplied from user mode, right? So a user mode app is going to call a stub that will finally end up in this kernel mode code with the 3 parameters that they are controlled by the user mode application. And we are considering the user mode application as the attacker, OK? This is what it basically grabs the color from XY and returns and writes it to the buffer. What could go wrong? Well, what kind of checks do you guys think kernel mode is going to perform here? At least it's going to check if X is inside bounds, right? Y is inside bounds. But what about buffer? Buffers, I mean, what about if an attacker says, OK, buffer is in kernel mode? Is the kernel going to grab something from XY and store it in kernel? No, because that could be a memory corruption, right? Because of a user mode request, kernel mode write into kernel mode, no, that could be a security risk. So basically, this is an entry point. The main points is the parameters are controlled by the attacker, user mode app, and this is going to be executed in kernel mode, OK? Fancy pictures. So this could be a legit request. OK, give me the pixel at XY and store it in buffer set. But what about this? Give me a pixel at XY and store it in buffer set. What about if buffer set is pointing to a pool structure in kernel mode? You can cause EOP to kernel mode, right? This is the basics of the talk. I really want you to get this because we are going to cover more interesting things. Yes? No? Are you enjoying? OK, so what kernel should do? First of all, there are 2 main things that the kernel mode should do when they get a user mode request. Basically, they need to validate the request, and they need to capture the request if it is necessary. What do I mean by validate the request? If kernel mode should return some data, it should write the data to a user mode buffer. Kernel mode must be sure that this buffer is located in the user mode and is never located in kernel mode space. Why? Because because of a user mode request, we're going to corrupt kernel memory. That could be a security vulnerability. How the kernel mode does this? So basically, there are several mechanisms, but I'm going to cover pro for write, pro for read, handle validation. Basically, pro for write is going to validate a range, a starting address plus a length, if all the pages on those range are located in user mode, and if those pages are writable. If not, they are going to raise an exception. And if you guys are familiar with kernel mode, an exception in kernel mode that is not handled, back check. Pro for it is similar, but they don't do the check for writable pages. And handle validation, I'm not going to cover in much detail handle validation, but you can think about kernel entry point that is expecting, I don't know, a menu handle, and you provide a file handle. You have to be sure what kind of handles you are using you're treating. The second thing that you should do is capture the data locally. What do I mean by capturing data locally? For example, let's say that in kernel mode there is an allocation and a later copy, and the allocation for getting the size of the allocation, basically you go to user mode and you grab once a value. Let's say 5. OK, you allocate 5 bytes. keeps executing code in kernel mode, and later you're going to do a RTL copy memory. But you go back to user mode and grab again that value. What about if that value right now is not 5? If a parallel thread in user mode changed the value? What about if at this point the value is 200? Basically, you have an allocation of 5, and you're going to copy on based on 200. It's going to corrupt the pool, right? So this is what it is called double fetches. So if you need a value, grab it once. Store it locally in kernel space in a stack or I don't know, whatever. But don't grab it twice, because you are not sure that the value is going to be the same, right? Time of check, time of use. For example, you are checking something, but the time of using is completely different, and race conditions. Double fetch is clear, hopefully. Yeah. So let's go. This is a pro for read, pro for write. 3 arguments: address, length. That's the range, and alignment. I'm not going to talk about the alignment. Basically, it validates the range if it is in user mode, and if not, it will raise an exception. Keep your eyes in the last bullet. If length equals to 0, doesn't matter what you put on address. It can be a kernel mode address, a user mode address, whatever. If there is if you read the pro for write, pro for read code, the first thing that they do is if address equals 0, return. Why? Legacy. There are several kernel components that they use this feature for exchanging the data. So keep an eye on this. If len equals 0, doesn't matter if address points to user mode or kernel mode. So common mistakes. Hopefully I've covered the basics for understanding the rest of the talk. If not, please stop me. I'm a friendly guy. Common mistakes, we have integer overflows, we have buffer overflows, whatever you can imagine on user mode, we have them in kernel mode, plus other things. So for example, for these next slides, I'm going to point to the vulnerabilities, but for the MSRC cases, I need your help. So pay attention to this. So for this one, for example, black can overflow here. There is a small allocation here because the size of the allocation can overflow. There is a null ref because we don't check new entries. Does anybody knows if a null ref in kernel mode is exploitable or not?
Sure as hell is on Linux. Don't know about Windows.
It is. It is. Does anybody knows how to allocate the null page on Windows? So basically, if empty virtual alloc, if you pass as the address as a null, it will return a random page. Well, what about if you pass a 1, a 2, a 3, something that is inside the first page? It will return the null page. So you can allocate. Then you perform a kernel mode request with the null page allocated. So basically, if you supply a big size and X allocate pool with tag fails, and you in your user mode app you already allocated the null page, you control new entries, the new entries structure, because it's pointing to user mode. And of course, if it was a small allocation, later on, based on the loops, you can perform a pool corruption. Same issues. It's not hell. We've been dealing with user mode for years. Kernel mode suffers them. So we need to pay attention for these things. Trusting user mode pointers. I don't know if you guys are familiar with method neither, method buffered. Method buffered, well, we're not going to talk about them right now, but let's imagine this entry point. The 2 parameters, they come from user mode. They are attacker controlled. Let's say that bar is null. There is no null checking. Again, this is fake code. We're going to later to go to real code. No probe for write on X. So for example, if we're going to return data to the structure bar, we need to probe for write it. No length check. Probably bar was not allocated with a sufficient length, etc. As I already told, null derefs are exploitable in Windows, same as Linux, as Spender showed us during this month. So, for example, for method buffer is a method for communication between user mode apps and drivers through IOCTLs. With method buffer, basically the user mode app will say, okay, this is my input buffer length, and I expect the results in my output buffer and output buffer length. The kernel, before giving control to this function, will copy input buffer and the length to system buffer. But what about if the user mode app does not supply any data? System buffer can be null. We are, for example, we are assigning a stats structure to that system buffer, and later we are dereferencing the version member of that structure. That's a null deref. What about if we control the null page from on the user mode application? What about here? We're going to perform a write AV. If we control the data pointer, we can point it to a kernel mode address. That could be a write AV, a controlled write AV in kernel mode. So here's the deal. Pro for write, pro for read can be bypassed with length 0. What about here? Let's consider that W param and L param, they are user controlled. When I say user mode control, it's attacker controlled, right? So here, for example, string.maximum length gets assigned to W param, and then it gets multiplied by 2. What's going on here? What about if I put in W param 0x80000000? What's going to happen if this value gets multiplied by 2? It's going to become 0. It's going to overlap, right? Whoops, no, sorry. This can overflow, right? What about if we put in L param a kernel mode address? We are going to probe for write string.buffer L param kernel mode address with 0, and we don't care about alignment. It's not going to generate an exception because even it has a kernel mode range, the length is 0. It's going to pass it, okay? And let's assume that later there will be a write W param T chars. So there could be if you're pointing to kernel mode, you're going to override that kernel mode range. So this is a way to bypass probe for write with length 0. Another way that I've seen is what about if there is a mistake, there is a vulnerability where we probe for one length and we later copy based on another length. So for example, for this one probe for write, let's consider output buffer and output buffer length attacker control. Let's say that we put in output buffer a kernel mode address, and let's say we put in output buffer length 0. We bypass the probe for write because it's a length 0, and later on the RTL copy memory is being done based on another length. It's going to write into that pointer another length. It's going to perform a memory corruption, probably a pool corruption. So probe for write with length 0, probe for write with checking with one length and using a totally different one. Oh, sorry about this. Is this clear? Any questions so far? No? I need interaction. If not, no Windows source code. So casting truncation. This is pretty similar to the previous one. Basically, what about if a parameter that comes from user mode, you truncate it to 16-bit, and later you use a 32-bit. So string maximum is going to be truncated to a 16-bit. So what about if I put FFFF0000? It's going to get maximum length is going to be 0, and we're going to probe for write a pointer, attacker controlled, with a 0. But let's imagine that later we are going to write based on W param. This one is clear? So let's continue. as I already told you guys, what happens if pro4write finds a kernel mode address with a length not equals to 0? It will raise an exception, right? What about if there is no try catch, try set, try whatever? It will backcheck. I've seen source code that they are doing the validation correctly, but probably was never tested. So supplying a kernel mode address with something that is not equal to 0, it will backcheck. I don't know, probably it's the USB USB bugs. So basically here W param, L param again, they come from user mode. Pro4write will generate an exception, but it's not there, the try catch, so it's going to generate a backcheck. Even if we bypass the pro4write somehow, we need to put inside an exception handler, inside an exception handler, all the accesses read and write to the data, the user mode data. No exception handling, backcheck. It's okay? So this is the double fetch that I was talking before. This is the case that we go several times, commonly twice, to user mode for grabbing the same value. So for example, for this one, let's say that L param and W param, they come from user mode. We basically cast L param to my struct, so my struct is pointing to user mode. Let's assume that it is already validated with pro4read, pro4write correctly, etc., but not captured. So it's pointing to kernel mode. It has never been fetched from user mode to kernel mode. First use, my struct CB data. I'm going to grab for the first time this integer. Let's say, again, the first fetch is 5. CB capture is going to have a value, size of my struct, let's say 10 plus 5, 15. We're going to perform an allocation based on that size, 15. Let's say we succeed on the allocation. We have a small memory. My alloc is pointing to it of size 15. But what about if we go again to user mode and that value at this point is 200? We're going to copy to my alloc that the length of the my alloc allocation is 15, but we're going to copy 200. Pool allocation, right? Anybody familiar with pool allocation exploits? Double freeze in kernel mode? Yeah? Okay. So is this clear? Don't go twice to user mode. Just basically grab it, store it in a local variable, and use it whenever you need. Don't go several times to user mode, right? So MSRC cases, I need your help. Anybody remembers MS0801 IGMP? Who was the finder? No, I'm kidding. It was Mark Dwod, as far as I remember. He was working for the X-Force, and he reported the first TCP/IP vulnerability in Vista for IGMP. Where is the vulnerability? I need someone to tell me this here. It is pretty similar to one of the fake source codes that I already. Anybody over there? No? Okay, I'm going to give you 10 seconds more.
I think it double fetches from user mode via the address point.
Well, let me say that the IGMP address and the address pointer comes from network. It has nothing to do with user mode. This is the only example that has nothing to do with user mode. This is an example of common old mistakes. So it's not a double fetch. Okay, I'm going to show this quickly. Should I show something else? Yeah? No? What's going on there? What's happening there?
What is the record underscore size macro?
Which one?
In the ctalloc command call, that record underscore size macro?
Let's say that it is a multiplication between count and a size of something.
Okay, that could overflow.
Yeah. But let's say that count is bounded, because count is a U-sort. And let's say that the size of is going to be 6. Then it's, yeah. So let's say that we have in the IGMP packet more than 65K addresses. I mean, you can trigger this through multiple IGMP packets. Count is going to overflow, right? Once you reach 65K, next one is going to be 0, right? So here we have a small allocation because we overflowed it, and for example, we have right now 2, but in reality it's 65K plus 2. We perform a small allocation, and the bug was that later we were going to copy based on 65K plus 2. The fix here, this is real Windows TCP/IP source code. The fix here was to do a basic integer overflow check on count. Is this clear? No? Why not? Any question?
Yeah. I can't understand why source list may contain so much entries.
Let's imagine that
Coming from networking.
No, but let's imagine that there is a preprocessor before this function that will add all the packets, all the IGMP addresses that comes in a time frame into one list. So this is not only one packet. This is several packets that they gathered all the addresses and they put them in one list. So there can be more than 65K. Trust me.
Yeah.
I'm a trustable person.
I think the error occurs on the Windows Media Streaming Server. Yeah, maybe. Yeah, I believe it.
Trust me, I'm a trustable. No, well, my family trusts me. So basically, this is an integer overflow that leads to a small allocation that leads to a pool corruption. Win32K. Okay, this is purely user mode request to kernel mode. This is pretty similar to one of the source code that the fake ones that we already saw. Where is the vulnerability here? It's pretty much the same. Should I give you hints? No? Okay, so, well, no. So basically, you could say, okay, same thing.
Maximum length is multiplied, and if it's a correct fraction of to the power of 16, whatever it is, then it will get hit.
Yeah, that's correct. That's correct, but close to be correct. So let's say that you don't know the definition of large string. And let's say that in this particular case, it was not the multiplication overflow. It was because maximum length was described as a 31-bit. So there is a truncation, and 80000 becomes 0. So even if it was at 32-bit long, there was going to be an integer overflow in the multiplication. But in this case, it was the casting. Yes? Probe for write by pass, we pass a kernel mode address with the casted length that leads to 0. Let's say that later there is a RTL copy memory based on W-param. So how much time do I have? Okay. I'm going to go quickly. This one, afd.sys. Basically, I'm going to give you a quick hint. This is the length probe not equals to length used. We are going to validate this against output buffer length, that is attacker control. If we put there a 0, we bypass this probe for write, but later we are going to copy based on another length. Yes? No? If we put there a kernel mode address, we're going to write to that kernel mode address. ALPC, I can tell you, well, this is a bit difficult because you don't know the the definitions of ALPCP get owner port message. So basically, this is an direct. This function can return null. The assert is not being executed. So basically, if you allocate the null page in the user mode app that is calling to this code, basically, if that call fails, you own that structure, owner port, and here there is it's going to be a read AV from null page. So this is a null deref in kernel mode. All these cases are at least 1 year old, so no fear here to be exploited by those. This one, this is a double fetch. This is easy. Clear? First fetch, allocation based on that fetch. Second fetch, RTL copy memory. This is real Windows source code. So what we did for fixing this is basically grab PCDS reference to CB data locally and basically change the two reference to that local variable. So this is the part that I'm going to outline several tools, several free tools that they are outside there, mainly by Microsoft, developed by Microsoft. First of all, DevCTL is an IOCTL fuzzer that is included in the WDK. WDK is kind of a SDK for developing in kernel mode. It was developed, this tool, by Neil Clift, and in the latest WDKs for Vista, for Windows 7, there is an improved tool on that one called DC2. Basically, with this one, there is a number of switches that you can say, okay, fast these APIs, fast these IOCTLs, etc. If you are developing in kernel mode, use it. I mean, it's integrated in your development lifecycle. It's free. We're not going to charge you. Driver verifier. So the interesting part of this is driver verifier is already part of your operating system. If you basically run verifier.exe, you are going to see a nice GUI for enabling and disabling several switches in the OS. Basically, the thing that I love most from driver verifier is the special pool. Who is familiar with page heap in user mode? Okay, one. So page heap is a nice technique to detect the root cause of heap overflows. Basically, page heap in user mode, whenever you request an allocation, it will put a guard page in the back, in the beginning of the before the allocation and at the end of the allocation. So if you perform a heap corruption, it's going to heap the guard page. So we have kind of a similar thing in kernel mode. That's called a special pool, and it can be enabled through verifier.exe. There are several other switches. I suggest you to play with them a little bit. There's handle verification, etc. If you are going to fuzz your kernel interfaces, it could be wise to enable them. It's going to save you a lot of time triaging the cases, looking for the root cause for them, etc. Static driver verifier. This integrates with the WDK. Basically, there are several checks in the source code level that integral overflows, special. It's a compile time plugin. Two commands to execute. It's free. Use it. If you are developing something on top of WDK integration, there's a lot of documentation on MSDN to use it. Of course, it's a new trend. The static analysis frameworks. You can develop plugins to detect. There has been a lot of development of plugins to detect stuff on user mode, integral overflows on allocation, etc. So they can easily be applied to kernel mode. I can imagine on integral overflows on allocation, pro for read, pro for write bypass, the length 0, the length used against the length that is later going to be copied against. Method buffered, method neither, all the usage of these pointers without previous checks. All this can be probably easily catch through static analysis. These are the door points. What I hope you get from this talk is that it is pretty easy to make mistakes. Probably it's easier to make mistakes in kernel mode than in user mode. Extra validation is really needed. They are tricky to find, but we have tools, we have existing tools that they can help you. And please, fast your interfaces, apply any security checks to your interfaces. Thank you guys. Thank you for coming here. These are the people that helped me, Microsoft, Bruce Dunn, Matt Miller, Damien Hayes, Andrew Ross, Thomas Garnier, several other non-Microsoft people, Sexy Pandas, Matthew Switch. You can contact me here or Twitter or whatever. If you have any questions.
You said that this special case length equals 0 in proper write is legacy stuff. Why did Microsoft years ago create a proper write 2 which doesn't have this feature and get all new code use that one?
So in future OSs, it is being discussed to change this API, but we cannot break, for example, Apple.
You don't need to break. Get a new one, a second one, and tell all developers use the new one, so that all new code uses the correct version.
I will take.
That is not so hard to do, please.
I will take your suggestion, and I will go to the kernel guys for this. But it has to go through a lot of testing, so I will take your suggestion.
I guess this is sort of related to the previous question as well. The fundamental problem with most of those isn't that probe for write returns on 0. It's that the probe for write argument and the RTL copy memory arguments are different. Because if you probed with 0 and then you copied 0 bytes, nothing would happen.
Yeah.
So is there some standard helper function that just combines the RTL copy and the probe for write into one call? Because it seems like that would get rid of literally half the problems you've shown us.
No, there is not. And there is one reason, because you can have several code that you need before in between those functions.
You can always use it. But
Probably.
You could use it. It would solve half these problems.
So the answer is there is no such macro. Could be useful.
Any further questions? Otherwise, thank you very much.
You're welcome.
And we can have some further discussions at the coffee break, which is now. Thank you.